Okay, here's the last section of the confidence interval unit. Today we're going to be talking about section 10.2, and this is two sample t intervals, or two sample intervals for the mean. Now, this is a little bit different from the 9.3, which also had two columns of data, so you have to be careful which one is which. The 9.3, the matched pairs, is when you had two dependent samples. So, for instance, in the depression scores with caffeine versus without caffeine, you had people who were more depressed or scored higher on the depression scale without caffeine would be more likely to have higher scores with caffeine as well. Whereas the two sample is two different independent samples. So you're not going to have any one person in both samples or in both treatment groups. If they're in both treatment groups, it has to be matched pairs. If you have two independent samples, so I'm going to sample men versus women, or young people versus old people, then that would be two separate samples. No one person can be in both categories, and therefore I would use the 10.2 formulas and conditions, which are just a little bit different. So here are some other examples. So if I wanted to gather opinions about Democrats and Republicans over state gambling initiatives, so I'm going to take one sample of Democrats, one sample of Republicans. I could have some people that do not identify as either, but I'm not going to have anybody that identifies as both. So that therefore it is a two sample example. If I have any kind of experiment where I have two treatment groups and everybody is only going to get one of the treatments, there's no pairing whatsoever, then it has to be two samples. So new cholesterol medication in men versus women. Okay, so two separate groups. Or if it was two separate cholesterol medications, an old one and a new one, even if it was given to all different gender or age and whatnot. There's two separate treatment groups. That would be another example of two independent samples. Testing reaction times between retirees and kindergarten students. Nobody's going to be in both groups, so it's two sample. So here's some practice we did in class. We have plots of land, 10 plots. Each plot of land is going to be divided in half, and I'm going to plant both varieties of tomatoes in each plot. So because each plot of land gets both treatments, it has to be matched pairs. Now, if you read that a little bit differently, this is something that came up in class, if you read that a little differently, that half of the 10 plots, meaning 5 of the 10 got one variety and 5 of the 10 got the other, that's two separate treatment groups, that's when it would be a two sample. If I'm comparing IQ scores, low income versus high income citizens, that's two sample. You're going to have nobody in both categories. Birth weights of mothers, of babies whose mothers did not participate versus those who did participate in a prenatal program, to sample as well, as long as, and you'd want to make sure that the researchers were the ones that were assigning treatments, so it was an experiment, in fact, but that would be a two sample interval. Testing reaction time versus left versus right, on the other hand, would be matched pairs. So if I'm going to do left versus right hands of the same person, that would be a matched pairs design. Okay, so if I want to do a two sample t interval, here's what I'm going to be looking for. The shape will be approximately normal as long as it either says that the populations that the samples are coming from are known to be normal, or each sample, meaning both of the samples, have to be at least 30 by the central limit theorem if the normal condition would be met. Or I would have to do a normal probability plot, just like with 9.3. However, with 9.3, I would do a normal probability plot of just the differences. So one normal probability plot. On 10.2, I would have to make a normal probability plot of each group. Okay, so I'm going to have two plots. I'm going to draw two graphs on my page and comment on the linearity of each of those. The estimated center for the difference between the two means would be at the difference of the two sample means. And then the spread would be this formula right here. So once again, the combined spread of each under the root, because we've moved it from variance back to standard deviation. Once again, that is on the formula sheet for you. Okay, so whether you have sigma, meaning population deviation, which would actually make it a two sample z interval, which doesn't happen very often, or if you have S, which is the more common, meaning I have the sample standard deviation, but otherwise it's the same formula here for the difference of sample means. Okay, the conditions You need, once again, random, normal, and independent. Both samples would need to be random, or the treatment groups would need to be randomly assigned. We've already discussed what it needs to complete the normal condition. And then for the independence, once again, either it meets the 10% condition, mostly for samples, or the responses of samples or groups are independent of one another. If you don't know the size of the population, that's the one I would fall back to. The formula for the two-sample T interval is what I'm going to focus on because that is the more common one, is the difference of the sample means is our point estimate for the difference of the population means, plus or minus the t-star. The t-star, once again, is based on both the confidence level and the degree of freedom. Now, since I have two different samples, I could have two different sample sizes. So the conservative estimate for the degree of freedom is you take the smaller sample size minus 1. Okay, so if I have a sample of 10 and a sample of 20, then I'm going to have 9 degrees of freedom because I would take the 10 minus 1. That would be the degrees of freedom I use to look at my t-star. The smaller the degrees of freedom, the smaller the sample size, you're going to have a larger t. So it's considered a conservative estimate because that will always give you the wider of the interval. Wider interval, while it's less precise, would be more accurate, meaning more likely to capture the mean. And then here is the estimate for the standard error of the combination of the two distributions. If you had the rare case where the two sample z interval, the only things that would be different is that you would have a z star here, and I would not have to worry about degrees of freedom, and I would have sigmas in place of the two standard deviations, but otherwise no other changes. Two sample z interval would look very similar. So here is our first example. We have an old growth forest of pine trees. We're interested in whether the trees in the northern and southern halves of the forest are equal or not. So they took samples of 30 trees from each half and measured the diameter at breast height. So how wide the diameter of the tree trunk was at the breast height of the researcher, and went ahead and calculated the mean and deviation for each of those. We're going to construct and interpret 90% confidence interval. Once again, that means do the state plan, do conclude steps. So I wish to estimate at 90% confidence the difference in average diameter at breast height for the northern and southern halves of the preserve. Notice the 9.3, we're talking about the average difference, and in 10.2, we're talking about the difference in average. So subtle change in wording, but this indicates that we're going to average first and then find the difference, as opposed to calculating the differences first and then finding the average of that, which is what we did in 9.3. But like 9.3 and 10.1, since I am doing a subtraction somewhere along the way, I need to indicate which way I'm subtracting. So I'm going to do south minus north because, once again, I like positive numbers, and I see that just based on the sample means south has a higher average diameter at breast height, so I'm going to do south minus north. It would be totally fine if you did north minus south. Just make sure you specify that in your state step. So this is a two-sample T interval. Both the samples were randomly selected and can be considered approximately normal because both samples are 30. So remember, 30 or higher would be approximately normal. And then the sample diameter at breast height can be considered independent, since the diameter of the tree of one tree should not influence the diameter of the next tree that was randomly selected. Or since this is a forest, it would be reasonable to say that the 30 trees that were in the sample would be less than 1/10 of all the trees on each half of the forest. That would be 10% condition would be totally fine. So our estimate for the do step, our estimate for the difference mu1 minus mu2 is the sample mean for south minus sample mean for north, so 34.53 minus 23.7, plus or minus. Go to my t-chart for 29 degrees of freedom, since the smaller sample size was 30, actually both of them were. So I'm going to look up 90% confidence and 29 degrees of freedom, and I got 1.699 times the square root of the standard deviation squared for over the sample size for the first distribution, plus the same thing for the second distribution, and I get between 3.83 and 17.83. Okay, so I'm talking about diameter in centimeters. So then I can conclude I'm 90% confident that the interval between 3.83 and 17.83 centimeters has captured the true difference in averages in, I should have said, in the diameter at breast height. Okay, because this entire interval is in the positive numbers, we would be able to say that this provides some evidence that the trees in the south are wider. Okay, so they are larger trees in the south half of this forest. If the interval spanned 0, if for instance you had both positives and negatives in there, then you would say there is no significant difference in the size of the trees because the difference south minus north could be positive, could be negative, could be a difference of 0. And here's what this would look like in the calculator. Go to 2 sample t interval. Notice you have 2 options here, either data or stats. So in this one, we did not have the actual measurements for all 30 trees and both halves of we just had the mean and the deviation already given. So we chose to use stats and then typed in the mean, deviation, and sample size for both samples. Below this, I believe it will ask you if you want to pool your data. Just like before, you always say no to pooling. And then when you get your interval, you get this, what I have boxed in green. Now notice it is very close to what we got in our manual calculation. It is a little bit different though, and here's where you have to be careful if you're trying to do some kind of combination between the calculator and the formula. The calculator has input into it, it's one of the programs in the calculator, the big ugly formula that statisticians will use to calculate the exact degrees of freedom when you have more than one sample, so when you have 2 samples. So it's based on both the spread of the data, how spread out each deviation is, as well as on the sample size. It's usually a little bit less than the sum of the sample sizes, so the sum of the sample size would be 60. Here we got a degree of freedom of 55. So your options are either report the degree of freedom in the calculator, so 55.7 or 55.73 would be fine, and report the interval that the calculator gives you, or you can do, if you like the manual way, then you would report this with a degree of freedom of 29. So your degree of freedom and your interval should match. So either use 29 and the 3.83 to 17.83, or use the 55.7, 3.9, or 3.94 to 17.72. Okay. If you like to use the calculator, but you want to be able to get partial credit, so here's where you can kind of merge the 2 techniques. So option number 3, because if I just write down this number and something has gone wrong, I can't give you partial credit. What you can do is show the formula, but just put T star here. So I know that there should be a T value, but because my my chart is not going to give me 55.7 degrees of freedom, then what you can do is you can show this. So show that you know what the formula is for, that's where the calculator is getting the value, just leave the T there, then report the degree of freedom and the formula, the interval that you get directly from the calculator. So this is the way that you could use the calculator to actually do the big ugly calculations, but still get credit for showing that you knew how those numbers where those numbers came from. All right, last example, we have comparing the heights of 10-year-old boys and girls. We have the mean and the deviation for each given. I want to estimate at 95% confidence for the difference in average heights for the 10-year-old boys and girls. And I'm going to do girls minus boys because, once again, it looks like females have a higher sample mean, so less likely to deal with as many negatives. 2 sample t interval, both samples were randomly selected and normally come from normally distributed populations. So it says the heights follow a normal distribution, so we don't have to worry about sample size or anything else like that. Both the samples are pretty small, so it's reasonable to think that the sample is less than 1/10 of all 10-year-old girls and boys. Set up your confidence interval, so difference in samples, plus or minus. For smaller sample, -1 would be 7 degrees of freedom, so there's my t-value, and standard error. I get 95% confidence that the interval between -2.966 and +4.366 inches captures the true difference between 10-year-old girls and boys. Since this one does span 0, we have to conclude that there is no significant difference between 10-year-old boys and girls' heights, despite the small difference in the sample size. And go ahead and try the 10.2 problems and let me know if you have any questions.